Hello there, ATSEVS533 students. Dr. John Schrage here, and I am here today to tell you about Lecture 3B. This is the second day of our third module in the course, the module about modeling and what we can do with models and so on. And today what I want to talk about is specifically what we can learn from models about what the future of the world is going to be like. Now, last time we learned all about things like how models work. Well, actually, you have to combine that with that sort of 100 level class. But if you put those two pieces together, we learned all about how numerical models work. We learned about the different ensemble modeling strategies. We learned about how there were two different types of input to a numerical model. There was the so-called initial conditions, and there were the so-called boundary conditions. Initial conditions were, of course, the ones that were very important for numerical weather prediction. To determine where the big storm that's on the east coast of the United States today on the day that I'm recording this lecture, to know where it's going to go over the next 48 hours, you need really good initial conditions. The boundary conditions, things like the carbon dioxide concentration in the atmosphere and the output of the sun and things like that, don't really matter where that storm is going to be going over the next 48 hours. On the other hand, the boundary conditions are what makes the difference for climate simulation. If you're going to be determining what the climate of the world is like between the year 2100 and 2110, you're going to need to have really good understanding what the boundary conditions of the future are going to be like. The initial conditions that you start the model with, like the current weather today, does not have to be particularly well represented. Alright, so apparently what we're going to need is a set of boundary conditions that are going to be used to drive our numerical climate model. And we could ask ourselves what kind of information that's going to have to be, and well, we know it's going to have to be information like the albedo of the surface of the Earth. Not just the Earth as a whole, but like at each grid point in our climate model. This grid point that represents at this resolution an area maybe 10 kilometers by 10 kilometers or 50 kilometers by 50 kilometers. What are we going to use as the albedo of the surface of the Earth? And it probably won't be a single value. It'll probably actually be a value that changes with the annual cycle and so on. We're going to need things like the solar output, we're going to need things like the concentration of greenhouse gases in the atmosphere, and so on. And as a consequence, what you're going to see here is we have a lot of stuff we're going to have to know in order to run that climate model. Now, as we discussed, running a climate model is an enormous amount of work, not only in terms of the expertise of the people who are running it, but just in terms of the enormous amount of computer time involved. If you are a research team that is running a climate model for the US government or for the British government or for a university or something like that, you're going to be taking enormous amounts of effort to set this computer model up, to get it working right, to get the right inputs to it, the initial conditions and the boundary conditions, and then you're going to start it, and the dumb thing's going to run for 2 months on a supercomputer. Okay, you can't really do that lots of times. You need to make sure that you don't have a lot of duplication of effort. You want to make sure that the model runs that are run by different research groups are comparable with each other. You want to make sure that they are using, for example, the same boundary conditions when they conduct their simulations. That way you can take the research you did on the climate model at Creighton University and compare it to the model run that somebody else did at the UK Met Office, the Meteorological Agency for Great Britain. If you can't compare them because they don't have the same boundary conditions or they don't have the same, that's a problem. You can't really directly compare the two models. We need some coordination here as to how this is all going to work. And to facilitate this, organizations like the IPCC and other ones like AMIP, the Atmospheric Model Intercomparison Project, and so on, they defined various sets of boundary conditions that specify, in a kind of a standard way, different amounts of stuff in the atmosphere in the future. Where stuff could mean things like how much aerosol is in the atmosphere, how much carbon dioxide or methane or ozone or other greenhouse gases there are in the atmosphere, and so on. And we can specify this, and an independent outside group has said, we're going to say this is one scenario for the future. One possibility is we're going to have these greenhouse gas concentrations. We're going to have this much sulfur dioxide in the atmosphere. We're going to have this much sulfuric acid, sulfate aerosols. We're going to have this much mineral dust, etc. And all of this stuff is going to be specified in these. And if I want to run the Creighton climate model, there is no Creighton climate model, I can choose to run it using one of these standard scenarios, and my output will be directly comparable to the output of other universities or other government agencies that ran their model using these scenarios. But man, this is a huge amount of work to come up with this stuff. Because all of this stuff is really uncertain. It's going to take experts to know what will the mineral dust loading of the atmosphere be 50 years from now. Well, it depends on things like trends in soil moisture, trends in soil management, deforestation and use of forest land to become agricultural land. Things like, you have to take into account all kinds of sociologic changes, demographic changes, economic changes, technology changes, and so on, if you're going to know things like how much carbon dioxide is going to be in the atmosphere 50 years from now. This is all really complicated interdisciplinary stuff, but that's why we have science, is we can solve these kinds of problems. And organizations like IPCC and AMIP and so on have come up with these scenarios for the future based on the research of interdisciplinary teams, where they have come up with realistic ways in which the future could change over the course of the next 100 years or something like that. Now, from the point of view of what we're doing in this class, obviously things like trends in aerosols are going to matter, or trends in land use and albedo and so on, all of which is part of what those teams did. But let's focus on the greenhouse gas concentration, in particular the forecasts of what's going to happen with regard to carbon dioxide emissions from fossil fuels. What's going to actually determine what are those interdisciplinary teams looking at to come up with these future scenarios of what the greenhouse gas emissions in the future are going to look like? Depending on what classes you've had in your environmental science curriculum at this point, you know where we're going with this. We're headed towards the so-called IPAT relationship. But one term that is going to be determining how much greenhouse gases how much anthropogenic greenhouse gases we are emitting is going to be population. The human population affects how much greenhouse gases there are in the atmosphere. And that's not because we have respiration. Okay, I mean, it's true, we are breathing out a greenhouse gas, carbon dioxide, all the time, but that's roughly in balance with the plant-land biosphere part of the carbon cycle. Rather, it has to do with all of this technology. As world population increases, every one of those people consumes products that are produced and distributed using fossil fuels. They may, in fact, themselves be consuming, well, not literally consuming as in eating, but using fossil fuels for transportation and so on. As the world's population goes up, we can only be using more fossil fuels. Well, all else being equal, we'll be using more fossil fuels and therefore increasing the amount of greenhouse gases in the atmosphere. And of course, as you well know, the population of the Earth has been growing exponentially since the Industrial Revolution, certainly in the development of modern hygiene and modern medicine and so on. I mean, if you put the graph of world population on a scale that's, on the order of tens of thousands of years, you start seeing how dramatic the current, and frankly how unsustainable probably, the current spike in population is. Now, there's a whole branch of demography and sociology that's all about what's going to happen with global population. And there's a whole lot of uncertainty in that. I mean, like, here are different simulations. I'm not sure if on this, you probably can't read the captions here on the YouTube video, but probably if you get the actual PowerPoint, you can read them just fine. Or you can follow that link and get them yourself. But you can see that going out into the future, there are a wide range of different estimates as to what the world's population is going to be. The green curve there is the UN's so-called UN low for the United Nations low estimate, and the red curve is the United Nations high estimate as to what population will be over the next 100 years. And you can see the difference is, on the order of 10 billion people by the end of the 21st century. So, I mean, we have a lot of uncertainty on that. So when we make scenarios about what future greenhouse gases emissions are going to be, we're going to have to make some assumptions about what the population of the Earth is going to be at different times in the future. Now, our second factor that's going to be influencing the amount of greenhouse gases that are going to be used as boundary conditions for these future climate simulations is the affluence of the population, the wealth of the population. The more affluent a society is, the more energy it consumes to produce products and services, to have travel, to have medicine, to have electricity, or whatever. And as you can see, the world gross domestic product over the last, 200 years or whatever has only increased. surely you can see that the amount of energy that you consume is greater than the amount of energy your parents consumed at the same age, which is greater than the amount of energy your grandparents consumed at the same age. We have more electronic devices that use electricity. We have more electronic devices that took energy to produce and distribute. We have networks. We have the more affluent, we have more medicines that are very energy intensive to produce and distribute. The more affluent a society is, the more energy it's using, and we still get most of that energy from fossil fuels. But this is complicated, because, I mean, it's not just so simple to decide what the affluence of the future is going to be. It's going to depend on things like education for, around the world. It's going to depend on social justice around the world. Do groups that are currently disadvantaged move up as fast as people who are more advantaged? International security implications, places where there's wars and so on, use less energy than places that are having good economic times. I got this list from the IPCC document someplace. Ideas like rule of law and free trade agreements, access to technology. If there's good energy efficient technologies, but companies don't have access to certain markets to disseminate that technology, that's a problem. There's complicated ideas about monetary policy that are way beyond my expertise, immigration patterns, and so on. The point is deciding how affluent, what is the gross domestic product 20 years from now, what is the gross domestic product 50 years from now, is very, very difficult. In fact, again, we're going to probably need to have just different scenarios where we say, what if the rate of growth is this much? What if the rate of growth is this much? Now, in the past, all of these kinds of factors that I'm talking about here that determines the amount of affluence in our society varied quite a bit from region to region. Okay? Obviously, there are parts of the world that are more affluent and more energy intensive, and there are parts of the world that are less affluent and there are less energy intensive, and so on, which makes it really complicated to try to figure out from a global climate perspective how these values are going to change. At the present time, our best estimate about global changes in affluence are that the global domestic product will increase by about 2 to 3% per year for the developing nations, and only about 1 or 2% per year for the industrialized nations. But even the history of just the last few years tells us that there's wild variations from year to year and from one economy to another and one political regime to another and so on. This is complicated stuff. We don't have a single answer as to what the future will be for affluence. Rather, we're going to have to try different possibilities. What if we have a future that is more affluent in the West and less affluent in the East? What if we have a future in which the East has faster growth in affluence than the West, and so on? Our third idea about what's going to be influencing the amount of greenhouse gases in the atmosphere is technology. Now, this doesn't necessarily mean as in like iPads and computers and stuff like that. We're talking about like technology that reduces greenhouse gas emissions. Nuclear power plants, or technologies that scrub greenhouse gases out of coal-fired power plant emissions, or whatever. We're talking about, like, on the large scale, more efficient energy grids, for example. We're talking about that technology in that sense. That is going to be determining a large... We could still be very affluent if we are producing our things more efficiently with less production of greenhouse gases. Now, this greenhouse gas intensity is going to be a term that comes into this idea of technology. The greenhouse gas intensity is the amount of greenhouse gases that have to be emitted on average to produce $1 worth of goods and services. So you could take a given economy's, whether that's a country or whether that's globally, a given economy's total production of greenhouse gases, and you could take the total amount of goods and services it produced and divide one by the other to get the greenhouse gas intensity. Technology can be used to reduce that. Now, this of course is this idea of how we can combine these three terms into the IPAT relationship, more formally known as the Kaki Identity. I don't know if it's pronounced Kaya or Kaya. Kaya, I forget his first name, I think it's Hideki, is a economist, I believe, in Japan who kind of first articulated this idea. It is an equation that quantifies the total amount of emissions of greenhouse gases into the atmosphere per year, based on population, affluence, and technology, where population is going to be literally just with units of people. And A is global affluence, so it's going to be gross domestic product per person. So you're going to have units of like dollars per person. So when you multiply P times A, people times dollars per people, you just so far have units of dollars. And then T is that greenhouse gas intensity, which is tons of carbon per dollar. So PA had units of dollars, multiply that by T, you get, which has units of tons of carbon per dollar, you get tons of carbon. Okay, so this is going to be then figure out how much carbon is being emitted. Okay, that T is actually kind of a hard thing to think about. That amount of greenhouse gas emissions for dollar of economic production. It actually works better if you expand it into two other terms called EI and CI, where EI is the so-called energy intensity. Energy intensity is how many joules of energy it takes, regardless of the source, nuclear, clean, green, carbon, intensive, I don't care, how many joules of energy it takes to produce $1 worth of goods and services. That's closer to what we actually know from like statistics that come from factories and so on. Carbon intensity, then, CI, is the amount of tons of carbon it took to produce a joule of energy on the grid. Again, we don't care where that joule came from. Is it green? Is it from solar, wind, fossil fuels? I don't care. How much carbon did it take based on how much energy there is on the grid? And so if we were producing more of the energy not using coal, we would have a better value of CI, right? There would be less tons of carbon being used to produce an average joule on the grid. Why do we call it the IPAT relationship when T really needs to be expanded this way? It doesn't exactly roll off the tongue to call this the I equals PAEICI relationship, despite the fact that that's actually a more accurate way of, easier to think about it. And the really awful thing about that IPAT relationship, especially when it's been expanded this way, is that it makes it very clear about the trap we're in and how difficult it's going to be to fix our greenhouse gas emission problem. Okay, so there at the top of the slide, I've actually written out this equation expanded with the energy intensity and carbon intensity explicitly included. Okay, CI, the carbon intensity. We could work really hard to make incremental improvements in the amount of carbon it takes to produce a joule of energy, CI. We could do things like add solar power arrays to the energy grid. We could improve the efficiency of the grid itself. We could add green, but all that's just incremental changes. Okay, we can make small year-on-year improvement, and that's good. But we're not going to suddenly have this number get twice as good, right? It's small year-on-year improvements. That's a good thing, but it's not going to be a huge change. In the same sort of way, we can work really hard to make incremental improvements in the amount of carbon released producing energy. I think I have those two around. The energy intensity. Do I have those two around? Yep, sure enough. These should be the other way around, right? The amount of energy it takes to produce goods over there on the left, that should be energy intensity. The one on the right, where it says the amount of carbon released to producing energy, that should say CI. Sorry about the mistake there. Yeah, we can make incremental improvements as to how efficient your factory is and how little energy it takes to produce goods. That's good too. I'm glad we work on that. But here's the thing. If you actually look at this equation, we got a real problem. Even if we could make some small, and we should make some small improvements on EI and CI, no matter what, we're multiplying that by P, the population. A number that is always going up is going up exponentially. No matter how much we do to make tiny changes, or even not so tiny changes to EI and CI, we're multiplying it by a number that's increasing exponentially, and then we're also multiplying it by, which by the way is not necessarily a bad thing in the sense of like the ethics of it. I mean, we don't want global population to fall, certainly not in some horrible way. And then we're always multiplying it by A, the affluence, and improving global quality of life is frankly an intrinsic good. We don't want A to go down. We don't want people to be poorer. There's ethics problems there. See how the math is bad? No matter what, we have some fundamental problems here in terms of how this is going to work. I mean, like if I actually did, here's a graph from, I don't remember what source it is, but you can follow the link if you want it. We are working on energy intensity. there are economic incentives for factories to use less energy for production of goods and services, or for companies to use less energy, or universities to use less energy, and so on. And you can see globally and in individual markets, we are doing better at that. But that's an incremental year-on-year process. We're not going to change that overnight. Oh no. See how this is kind of a loser of a proposition? I mean, no matter what, frankly, even if we could drive the iPad equation all the way to zero, even if we could make all of our energy from green sources, that's just the amount of carbon dioxide or greenhouse gases we are adding to the atmosphere each year. If we could really drive this all the way to zero and get all of our energy from green sources, here's the problem. We would still be dealing with all the carbon dioxide we've already put in the atmosphere. And frankly, we can't even make I go down. It's very hard to reduce the value of I, since P and A pretty much have to go up. Which means we have to figure out how in the future to deal with that. This is part of the story of like why, for example, rights and education of women are so important. Things like that can produce changes in the curve with regard to population growth. Okay, that's one of the ways in which we can make this equation less terrible, is by affording more dignity to the role of women and things like that. And there's verbiage. Frankly, you have other classes where the sociology of this and so on is more clear. Before we move forward, I want to ask a couple quick questions about what we've learned so far. Question 1. The blank is a measure of what fraction of the energy we are producing from renewable sources. Is that affluence, energy intensity, carbon intensity, or irreversibility? Which of those terms there is a measure of how much energy we're producing from renewable sources? Make a choice from those 4 options and get a little feedback before you move on to question 2.